Welcome to Lesson 3, Introduction to PostgreSQL. In this lesson, we'll dive into the history of our database of choice, explore its unique features and advantages, examine its architecture, compare it with other popular RDBMSs, and point out a few real-world adoption cases. By the end of this session, you have a solid understanding of why PostgreSQL has been a major database player and why it might be the right choice for your next project. Let's begin our journey with a bit of history. I promise for the last time in this course. PostgreSQL's history begins in the mid-1980s at the University of California, Berkeley. It all started with a project called Ingress. Ingress, short for Interactive Graphics and Retrieval System, was developed from 1974 to 1985. It was one of the first attempts to implement the relational database model that had been described by our usual suspect, Mr. Edgar Code, in 1970. Like we saw in the first two lessons, the project was led by Michael Stonebreaker, who would later become a key figure in PostgreSQL's development. Ingress introduced QL, which stands for Query Language, a relational database query language based on tuple relational calculus. QL was designed as an alternative to SQL and had some unique features and syntax. Ingress was advanced for its time, but Mr. Stonebreaker and his team realized there were some limitations to the original relational model they put together. So they wanted to create something more powerful and flexible. In 1986, Stonebreaker started a new project called Postgres, which stood for Post-Ingress. Clever. The goal was to create a database system that could handle complex objects and extend the relational model. Postgres introduced many innovative features, including 1. The ability to define new data types. 2. The inclusion of inheritance in table definitions. 3. Rules for governing the processing of data. Postgres initially used PostgreSQL, an extended version of QL, as its query language. The journey from Postgres to PostgreSQL wasn't straightforward. In 1993, the original Postgres project ended at Berkeley. In an attempt to commercialize Postgres, Stonebreaker founded Illustra Information Technologies, which was acquired by Informix in 1996, naming Mr. Stonebreaker its CTO. In 2001, Informix database subsidiary was sold to IBM. Fortunately though, the mighty open source community saw potential to keep going with Postgres when it was BSD licensed in 1994. In that year, two Berkeley graduate students, Andrew Yu and Jolly Chen, replaced Postgres query language PostgreSQL with SQL, creating Postgres 95. By the way, I don't want to say SQL, so don't confuse you with SQL, IBM's System R former query language. We don't need to say Postgres 95 was no longer a good name in 1996. Therefore, the name PostgreSQL was adopted by the open source community, reflecting the biggest differential from its now commercial version of Postgres. This marked the beginning of the PostgreSQL as we know it today, a powerful, community-driven database system that continues to evolve and innovate. Fun fact, this also marked the beginning of a so confusing name, PostgreSQL, PostgreSQL, PostgreSQL. It's so frustrating, so that's why we keep calling it just Postgres. From now on, every time I say Postgres, you know they're no longer in the 90s. Now let's look at some key milestones in PostgreSQL's development. Postgres 6, released in 1996, marked the first version under the new name. It took 4 years until version 7 arrived, which was when MVCC was introduced. In 5 years more, before we saw the version 8 in 2005, which introduced save points and point-in-time recovery. Another 5 years passed before version 9 arrived in 2010, bringing built-in replication and hot standby capabilities. Notice how these early versions had significant time gaps between them. This pattern changed considerably in recent years. Postgres 13, released in 2020, enhanced performance for larger databases. We then saw version 16 released just 3 years later in 2023, introducing improved query parallelism and logical replication. These acceleration in major version releases reflect the growing community involvement and the increasing demands for modern data management. The Postgres community has been responding rapidly to emerging needs in areas like big data, cloud computing, real-time analytics, and artificial intelligence. Postgres has a unique set of features and advantages that have contributed to its popularity and widespread adoption. Let's take a look at some of them. Postgres is fully open source, which means its source code is freely available for everyone to use, modify, and distribute. This open source nature has fostered a vibrant community of developers, contributors, and users worldwide. The community-driven development model has several key benefits. First, it promotes innovations. New features and improvements are constantly being proposed, developed, and integrated by many people from all around the globe. Second, it leads to robust security. With many eyes on the code, vulnerabilities are often caught and fixed quickly. Lastly, it provides excellent documentation and support resources, as the community actively maintains and updates these materials. One of Postgres' strongest features is its extensibility. You can extend database functionality in numerous different ways. 1. Custom functions. You can write functions in various languages like SQL, PL/PG/SQL, C, Python, and more. Second, custom data types. You can create domains or entirely new data types to suit your specific needs. 3. Custom operators. You can define new operators to work with your data more efficiently. 4. Custom indexing methods. You can implement specialized indexing for unique data structures. We'll not only talk about indexes in a number of different lessons, but also have a dedicated one in section 6 from a performance perspective. Postgres supports a wide array of data types out of the box, including some advanced types that set it apart. JSON and JSONB, to store and query JSON efficiently. Arrays, to store multiple values in a single column. Store, which are key value pairs within a single value. Range types, to store and manipulate range of values. User-defined types, create complex data types specific to your application. These advanced types allow you to model complex data structures directly in the database, often eliminating the need for additional application-level processing. Postgres includes built-in full-text search functionality, allowing you to perform natural language queries on your text data. Key features include 1. Text search configurations for multiple languages. 2. Ranking of search results. 3. Highlighting of search terms. 4. Support for complex search expressions. Postgres extension ecosystem further expands its capabilities. Just to name 2 notable extensions we can highlight. 1. PostGIS. This extension adds support for geographic objects, allowing Postgres to function as a spatial database for geographic information systems, or GIS. 2. pgvector enables vector similarity search, which is crucial for machine learning applications and recommendation systems. These extensions transform PostgreSQL from a general-purpose database into a specialized tool for specific domains, all while maintaining its core relational database functionality. The combination of these features, open source nature, extensibility, advanced data types, full-text search, and powerful extensions makes Postgres a versatile, powerful choice for a wide range of applications, from small projects to large-scale enterprise systems. Postgres follows a process-based architecture, which sets it apart from many other database systems. This design choice has significant implications for how Postgres handles concurrent connections and manages system resources. At the heart of Postgres is the postmaster process, also known as the Postgres server process. When you start Postgres, this is the first process that launches. Its primary responsibilities include 1. Listening for incoming client connections. 2. Spawning backend processes to handle these connections. 3. managing various background processes essential for database operations. When a client connects to Postgres, the postmaster focuses on a new backend process dedicated to that connection. This means each client gets its own process, creating a level of isolation between different client sessions. This approach actually has both advantages and trade-offs. On one hand, it provides great isolation between client connections, enhancing stability. On the other hand, it can be more resource-intensive compared to thread-based architectures when dealing with very high number of connections. Think of Postgres as a busy restaurant kitchen, where different components work together seamlessly. The postmaster process is like the host or hostess at the restaurant entrance. They greet customers, client connections, assign them to available tables, and ensure each guest gets their own dedicated server, backend processes. Just as the host-hostess coordinates the entire kitchen staff, the postmaster orchestrates all database processes. Backend processes are like individual waiter or waitresses, each one dedicated to specific tables. When a customer or client makes an order or query, the personal waiter or waitress, which are backend processes, handles everything from taking the order to delivering the results. They work independently but coordinate with each other through the kitchen system. Shared memory is like the kitchen's preparation area and pass-through counter. The shared buffers are like the heater serving counter, where frequently used ingredients and prepared dishes are kept ready for quick access. The wall buffer is like the kitchen's order tracking system, recording every order and change to ensure nothing gets lost even if there is a power outage. When all these components work together, they create a robust and high-performance database system that can handle thousands of simultaneous connections while maintaining data consistency and reliability. In addition to our kitchen, Postgres employs several specialized background processes. Let's take a look at them. Writer process, which handles writing dirty buffers to disk. Wall writer, which manages the write-ahead log. Checkpointer, to perform the checkpoint operations. Auto vacuum launcher, which initiates a vacuum and analyze operations. And finally, stats collector, which collects statistics on database activity. Like we said before, Postgres implements MVCC to manage concurrent access to the database. MVCC is a smart technique that allows multiple transactions to read and write data simultaneously without need for excessive locking. Think of MVCC as a way for Postgres to maintain multiple versions of data, each associated with a specific point in time. This approach offers several benefits. Number 1, readers don't block writers and writers don't block readers. Number 2, transactions can see consistent snapshot of the database. Number 3, support for different isolation levels without significant performance penalties. In Postgres implementation of MVCC, each row in a table contains hidden system columns, including xmin, the ID of the transaction that created the row, and xmax, the ID of the transaction that deleted or updated the row. These columns help determine which version of a row is visible to each transaction. We will explore MVCC in much greater depth in section 6, where we'll discuss its impact on performance and how to optimize your queries with MVCC in mind. Write-ahead logging, or WAL, is a critical component for Postgres architecture, ensuring data integrity and enabling point-in-time recovery. The fundamental principle of WAL is that changes must be written to the log before they are applied to the data files. You can think of WAL as Postgres' safety net. Here's how it works. When a transaction modifies data, change is first recorded in the WAL. Once the WAL records safely on disk, the transaction can be considered committed. The actual data files are updated later in a process called checkpointing. The advantages of this approach are improved performance, as writing sequentially to the WAL is faster than the random writes to the data files. Crash recovery, as uncommitted changes can be replayed from the WAL. Support for replication, as the WAL can be shipped to standby server. In section 6, we'll dive deep into WAL configuration and tuning, exploring how to optimize it for different workloads and recovery scenarios. Understanding these architectural components, process-based design, MVCC, and WAL provides a solid foundation for working with Postgres. As we progress through the course, you'll see how these elements come into play in various aspects of database management and optimization. Now that we've covered Postgres architecture, let's compare it with other popular relational database management systems. Postgres and MySQL are both popular open-source relational database management systems, but they have some key differences. In terms of data types, Postgres offers a wider range of built-in data types, including advanced types like arrays, stores, and native JSON support. When it comes to concurrency, Postgres uses multi-version concurrency control without read logs, allowing for better performance in environments with heavy read-write loads. In terms of SQL compliance, Postgres adheres more closely to SQL standards, supporting a broader range of SQL features and syntax. While MySQL has traditionally been favored for being simpler and more appropriate for read-heavy applications, Postgres' robust feature set makes it more suitable for complex or intensive applications that require data integrity and more elaborate queries. Oracle is a commercial database system often used in large enterprises. Compared to Oracle, Postgres offers cost-effectiveness. Postgres is open source and free to use, while Oracle can be expensive, especially for large deployments. Extensibility. Postgres architecture allows for easier creation of custom functions and data types. And somehow related to the first topic is community-driven development. Postgres benefits from rapid innovation and community support, whereas Oracle's development is controlled by a single company. While Oracle has some advanced features for very large deployments, Postgres capabilities are sufficient for most applications and is gaining ground even in enterprise environments. Microsoft SQL Server is another major player in the commercial database market. Postgres distinguishes itself in several ways. Cross-platform support. Postgres runs on various operating systems, while SQL Server is primarily designed for Windows, although recent versions support Linux. Licensing. Open source license allows for more flexible use and modification. JSON handling. Postgres offers more advanced JSON operations and indexing capabilities. SQL Server integrates well with other Microsoft products, but Postgres' open source nature and cross-platform support make it more versatile choice for diverse technology stacks. As we progress through this course, you gain hands-on experience with many Postgres' advanced features, allowing you to leverage its full potential in your projects. Postgres adoption has been steadily growing across various industries. In the Stack Overflow developer survey, Postgres usage among developers increased from 33% in 2018 to 49% in 2024, surpassing MySQL to become the most popular database for the second consecutive year. This growth isn't just about popularity, it's about Postgres meeting to the evolving needs of modern applications and businesses. Postgres adoption spans from small startups to large enterprise. Interestingly, above 46% of companies using Postgres have fewer than 200 employees, while around 21% have more than 5,000 employees. This distribution shows PostgreSQL's capability and suitability for businesses of all sizes. As we wrap up this lecture, let's recap what we covered. In this section, we'll explore Postgres' rich history, from its origins in the Ingress project to its current status as a leading open-source database. We've discussed its unique features and advantages, including its extensibility, advanced data types, and full-text search capabilities. We've also looked at Postgres architecture, comparing it with other popular RDBMSs like MySQL, Oracle, and SQL Server. In the next lessons, we'll dive deep into Postgres features and learn how to leverage them in real-world scenarios. We'll start with our hands-on setup in Section 2, where you get to experience Postgres firsthand.